Okay, welcome back. I'm going to be giving this talk with Ryan, actually. I'm just going to give kind of more of an intro of the idea, and then Ryan will take over and talk more about the specific implementation. And I also included Jeremy Magland on here because he developed a lot of this and would be a good go-to person to talk about the specific technical details if you want to dig into this further. But we really wanted to talk to you about this new kind of radical idea that we have, this new way of thinking about data standardization that we call virtual data sets. So virtual data set is kind of the overarching kind of philosophy of this. And then LINDI is a specific implementation that Jeremy and Ryan have been working on, and actually the whole NWB team has been working on, integrating this with the NWB ecosystem to facilitate data standardization and efficient cloud access. So I just wanted to start off by giving an idea of the motivation behind this. So let's look at the current data standardization landscape. The most common way, I suppose, that people think about data standardization is standardizing a data format. So this is where you develop some format for how you want to represent data and metadata, and then you convert or organize data into this standard. Examples of this include BIDS, NWB, NICS, NIFTY. These are all either file formats or data standards that require data to be transformed in some way. So basically, you're going to take data in their source files and then manipulate them and copy the data and metadata into some standardized form. The benefit of this approach is you can facilitate universal access into the destination format. You can optimize this storage for read or write or the size of the files. You can optimize for cross-platform availability. But it has some downsides. It has some challenges. And anyone who's converted data knows these challenges well. There is overhead related to data conversion. You have to read and write the data, right? So that can mean a lot of compute, a lot of time. It can mean storage duplication. Maybe you don't want to delete those source files. Now you have two versions of the raw data. You have the source data, and then you have the standardized form. And on top of that, what if the standard changes? Now all of a sudden, do you have to rerun this conversion every time the standard changes? It becomes unwieldy, difficult to manage. And we've dealt with this. I mean, NWB is not static. It's changed through the years. We've got versions. We have 1.0 files that aren't compatible with 2.0. At a certain point, you kind of have to just make a cutoff and say, okay, we're gonna take the lessons we learned and we're gonna not allow for backwards compatibility, and we're just gonna start with a new major version of the standard. But that is it's a very difficult call to make, and it's also not without its downsides, obviously. If you want to access NWB 1.0 files, you want to use the latest tools, it's going to be difficult to do. And it fragments the field. And so we try our hardest not to do that, and we have tools now to mitigate that, the risks of that. But still, we have evolution in the NWB standard, and files that were created 2 years ago may not be quite up to spec with the latest versions. And so this is a challenge. Because of these challenges, because of the overhead, the data duplication, the difficulty in keeping data up to date, there's another approach to standardization which avoids all of these challenges, which is API standardization. So here you don't actually manipulate the data at all. And here you actually just create standardized software interfaces that can read from many different file formats. And there are libraries that some are dedicated to this specifically, and some just have a lot of this capability built in. So Neo is an example of this. That's a software library. Its whole goal is to standardize interface into dozens of different electrophysiology data formats. IBL1 is another example. They published a paper that said, hey, you can actually have data in any format as long as this interface works. There's a standardization effort called NeuroDataReHack that works in MATLAB that is an API interface. So you don't actually have to have the data in any certain data format. So this, as you can tell, is really advantageous for a lot of reasons. You don't have to copy the data. You don't have to maintain two versions of it. It's much easier to to change the standard, you don't have to then duplicate enormous amounts of data or do this enormous overhead of converting data. However, it has downsides. The biggest downside, in my opinion, is language lock-in. So this is basically like, okay, let's say you have universal access in Python Neo. Neo is a Python library. Let's say you want to access that data in MATLAB, or you want to access it in JavaScript. It can be difficult to do. And a lot of the developers of these platforms will say, yeah, but like everyone's using Python. Like you don't really, like who's really going to want to read it in another language? Okay, so maybe you might feel that way, but NDI is a similar project written in MATLAB who's making the exact same argument, but reverse, where they're like, yeah, we have this interface in MATLAB. Who needs anything else? Who would need to develop in Python or JavaScript or R or anything else? So it's like, well, you clearly can't both be right. Clearly there are fragmentations in the community, and maybe within your closed circle, that's perfectly fine. You know, we actually use Spike Interface a lot for this because they have a lot of reading tools for a lot of different libraries, which is fantastic if we're in a Python-specific application. But as soon as you go into something that requires R or JavaScript or MATLAB or Julia or anything else, maybe you can develop software bridges to those other libraries, but those are very fragile and I wouldn't recommend relying on them. So yeah. There's language lock-in, which makes things fragile. I would say even if you're willing to stay within the same language, if you develop an API and then you try to go back 5 years later and you haven't been maintaining it, the software ecosystem around that API will likely have changed. Maybe you built it for Python version 2, and now there's nothing supports Python version 2. Maybe you built it for Python version 3.8 and you can't run it anymore, right? There are numerous examples of software that worked perfectly fine 5 years ago, were untouched, and now cannot be used without significant effort. So it's not a great solution for archiving data because of that, because it doesn't have that longitudinal support. On the other hand, if you do the format standardization, you have longitudinal support because at the end of the day, even if the APIs to read those files break, you can develop new APIs. The data itself is still there in a standardized way. And if you just adjust the APIs, you should be able to read all of this data. So we have serious pros and cons on each side. We have the burden of data conversion on the left, but the benefit of stability. And on the right, we have it's much easier and doesn't require this overhead if you do an API standardization, but then you're locked into certain compute ecosystems, and it's not clear if this will have longitudinal support. So I wanted to present to you a solution that gives you the best of both worlds, and that is virtual data sets. Okay, so here's the idea of the virtual data set approach. It is that you leave the source data as it is, but you create these maps into those files that tell you exactly how to read the data in a standardized way that can work across data sets. And these maps, they contain references to the data sets in their original files, and they also provide the ability to add structured metadata. So the way you, getting into the details of the implementation is what we're using is a JSON file that uses the ZAR specification. So ZAR wasn't built for this, actually. It was built to be a data standard, but it has its own language for representing how data is stored. And that has become kind of a standard in the field for representing data storage. So if you have a binary blob, you can say, okay, this binary blob has the int16 data type. It's like this shape. It uses this compression algorithm. It has a standardized language for expressing these things, which you can use outside of ZAR source files. So then you have this JSON reference. It maps to original data locations. It maps those original data locations to a standardized schema, which could be the schema of your choice. We will use NWB, though that's not specific. Virtual data sets are not specific to NWB. This has the advantage of it works across programming languages, because all you would need to do in any programming language is read that map. And then all of a sudden, you have the ability to read any file that is represented using the map. Now, of course, you do need to develop the API to read the map. And that's a non-trivial amount of work. But once you put forth that initial effort, all of the rest of the data follows. This has the ability to enable cloud-native access patterns. So one of the challenges of HDF5, though it's possible to get around it, well, I would say the challenge of HDF5, one of the challenges is that the C library to read it is very complicated and heavy. And it can be difficult to optimize it for your use cases. I think that's a fair thing to say. Now, if you really know what you're doing, you can get a lot out of it, but there are much simpler ways to read this data. If you're able to represent it in these types of maps, you are not locked into the C library, and you can use other patterns to read the data, which allow you to much more easily create parallel access patterns to the data. So basically, you can think of this of creating a universal translator that any software can use to understand your data, as opposed to changing the data itself. Can you guys see this in the back? The red sometimes is hard, but this projector is pretty good. Okay. So I'm going to give you kind of a simplified example of what this looks like. So this is the map file. This is a JSON file that is all of the metadata fields you would need to read the data. So here we have some initial information about the ZAR format. We have pose data, and then there's this .z array, which tells you that we're storing metadata about an array. And it has the shape, the data type, the chunks, and then array dimensions, which is actually metadata that corresponds to the Xarray library. And it tells us, OK, if we're reading this in Xarray, we're going to label the dimensions in this way. And then on top of that, there's an attributes, which then you can add whatever you want. Here we have got units, body part labels, coordinates, sampling rate. And then finally, we have telling offering the link to the actual source data. So we're saying, OK, the source data is here, this relative path, this file offset, and it's this long. So basically, using this information, we're able to read this data, OK, this chunk of data. And then so this file could be locally on your computer, or it could be accessible at a URL where you say, OK, go fetch the data, and then use this offset and this size, and then you're just going to pull that chunk of data if you ever want to access this. And then here's another example. Let's say you also had depth information as a three-dimensional array. It would look like this. You have a different data type, which is an unsigned integer. And here, let's say you're using different chunk sizes, which is, you're saying, OK, this data is laid out in specific smaller chunks. And again, you have units and array dimensions. And here I just want to note this file path is different from this file path. So here we're aggregating data from multiple different files into one virtual data set. And we don't need to combine them into one HDF5 file, one big HDF5 file. And then here, again, we have another data set. This is just one-dimensional. And you've got some bin data. And we're saying, OK, it's a float. And here's how you would read that data, 0 offset, and then you just put the size of the file. So here again, you can map multiple data sources in a unified structure. You can preserve original metadata and relationships, right? So that means if you're worried about, if you're doing the data standardization approach and you create, let's say, NWB files, you may be worried that not all of the essential metadata has made it into the NWB file. And because of that, you might be reluctant to delete your source data, understandably. With this approach, you're keeping your source data as is. So if there's any essential metadata that you didn't manage to pull out, it's still there. I mean, it will require you to have specialized code to pull it out, but at least you haven't deleted it. This works with ZAR-compatible tools. So it will work out of the box with ZAR. I mean, it takes a few extra lines of code to get this map to work, but it's really quite easy to do. And it enables you to add metadata, add any metadata you want, and in a structured way. So you could say, I want this map file to follow a certain schema, right? So that means my source data doesn't have to follow that schema. I just need to map it into that schema. And this allows me to add, let's say, this metadata, for instance. My schema might require this metadata. So now I can just add it here instead of adding it to big data files. And this also has the benefit of separating out your data and your metadata. So if you need to edit your metadata, you don't necessarily have to edit these huge files. So essentially, this approach has solved a lot of the pain points of using large HDF5 NWB files. We don't have these massive files that if you want to just edit one little piece of metadata, you have to change the whole file. We don't require data duplication. We don't require the overhead to do this data conversion. So what are the downsides? Well, this approach doesn't always work. If you have proprietary formats that require special software or libraries to read, you can't do this. If you have inefficient data storage layouts, so let's say you have like 1,000 channels and then each channel is represented in its own file. That may be inefficient for certain workflows, and just describing the map is not going to help you with that inefficiency, right? You can get a much more efficient, you can store the data in a way where you can read it much faster in certain read patterns if you allow yourself to read the data and then rewrite it in a more efficient way. So this doesn't help you with that. And it doesn't allow you to access data where the formats require sequential reads and don't have random access abilities. It really requires the data. It has certain constraints around the types of data representations that you're able to express, right? So if you just have a binary blob with a standard data format, then we can represent it. We can go further than that. We can represent chunks, and we can even represent chunks that themselves are compressed if the compression algorithm is supported. But currently, that's the limit. Like you can't, you would need to build more and more capabilities, and then of course, it's more and more difficult to develop an API that's able to read it in multiple languages. So there's a kind of a trade-off there, and we just can't represent every type. I would say our biggest type of data that we have found has not been representable in this way is data where it's chunked and the chunk sizes vary. So if you have one array that has multiple different chunks, but sometimes those chunks are big and sometimes they're small, we can't help you with that because we assume that all chunk sizes are the same. Welcome.
Two questions. So the first one is how is this compatible with LINDI? So to go on LINDI,
Yeah. Yeah, it's okay. Yeah. It's not.
Okay. I can get into it.
Yeah. I'm talking about this as a way to standardize data. And yeah, there are certain workflows where, like, let's say you wanted to do this locally, and then before you upload to Dandy, you do the conversion. So in that workflow, it is, but only because you've kind of manipulated the workflow for it to work. But we also do this on read. So you can index an HDF5 file, and then use this virtual map of an HDF5 file. Now, it's already been standardized, so it's not really helping you with the standardization aspect, but it does help you with the read aspect and the cloud access aspect, which is mostly how they've been using LINDI, though we're working on also using LINDI to like aggregate data sets together, so we are using it in a compositional sense as well. Yeah. Right.
So, if I understand correctly, here you still need to rely on, like, so there are two advantages or just features. One is that it's a specific map for my data set, right? It's not a map that is
right.
A generic for a bunch of these. Oh, yeah.
That's right.
So, yeah, thank you. So I still have to write it. So
you have to write
in the API. Yeah. I can just rely on the API and importing data from.
Yeah, every data set, every virtual data set has its own JSON map file.
Its own JSON. Yeah, and then the main advantage is that, like from how I'm understanding it, is that it relies on JSON, right? Instead of relying on a specific programming language.
Right.
Right.
That's right.
Okay.
It's describing the read pattern in JSON, which can then be interpreted by any supporting library. So this requires us to build out a multi-library ecosystem that can read the JSON.
Right.
And we're working on that.
Yeah, less effort compared to the APIs that have to completely convert.
Yeah, exactly.
Okay.
Yeah. So it's basically creating a standardization point in the file system in the form of this JSON file that doesn't require you to copy the underlying data. Yeah.
Maybe this is what you meant just now. Just to clarify, if you have data sets shared on other platforms, like BitShare, some people publish their data
Yeah.
And then you just have like a JSON file specify how that maps onto an NWB format, and then you
Yeah, you could totally do that. If you're storing the data in a compatible way, you can totally do that. If you have like a URL that is universally accessible and doesn't require login, and if the data format that you've chosen is compatible with this approach, which, like, for instance, in theory at least, .mat files are compatible with this approach, usually.
Okay, is there like a list of format that is compatible with this approach anywhere?
No. We're working on it. I guess that would be a good thing to do. Yeah, it's a good idea.
Yeah, because I've seen some so I look over some Datasets. They also share the data on Figshare, and then that structure they stored can be run directly using their GitHub code. But that is not the NWB structure. I think they shared like both, just so you know, required. But I think it will be massively helpful if there is a way to kind of uniform these kind of access to make things clearer.
Though I will mention, it kind of feeds into one of the points here on this slide. Actually, we've kind of covered both of these. So, Marco, to cover your point, you can use virtual data sets where possible and then convert when necessary. So if that's what Dandy requires, you can just convert it. And that allows you to optimize the data layout on submission, which is the main reason why Dandy doesn't support it, because they really want large data sets to be compressed. And a lot of these source formats are optimized for write, not for read, and are not compressed. And so then you end up with really inefficient data storage in the cloud, which they don't want. And then the other point is, if you're going to do referencing of external files that are in another database, you really have to worry about data persistence at that point. Because if you're pointing to another data set and that data set changes or disappears, these maps are completely useless. So you really need to have some sort of assurance, and that assurance can be in the form of you manage those source data yourself, or it's under some sort of system that has very clear governance principles where you know exactly under what conditions a data set would change, and you're able to like respond accordingly. Yeah. And that's the intro. I'll pass it over to you, Ryan, for how we're implementing this in PyNWB.
Any questions on philosophy?
Yeah, go ahead.
I really like this idea, and also zooming out a little bit further. So instead of thinking about like one session, thinking about an entire experiment represented as a virtual data set, and it really solves the problem of being in a lab with like 15 disparate experiments that are saved in different folders, and I don't know, it just seems really good at the level of you have one of these per experiment. Yeah, that's all. A comment maybe.
Yeah, so we see a lot of the benefits of this approach, the virtual datasets approach, for NWB, for neurophysiology, and we've been experimenting with how to make this happen. A lot of this work has been done by Jeremy, but also with contributions from the rest of us. And yeah, so as Ben mentioned, yeah, most NWB data right now is in this HDF5 file format, and it's just one big monolithic file that can be hundreds of gigabytes and holds all these different groups and arrays within them, and all of their metadata distributed in these different places. This results in big files that some of you are probably hesitant to download to do analysis, and so you're using streaming methods. And some of those streaming methods are more efficient than others, but generally it involves opening the file, connecting to Dandy, and making lots of little requests for chunks of data back and forth and back and forth and back and forth. And this includes for metadata, and this is for all of your array chunks as well. And if you want to, one, this can be slow, and two, if you want to query metadata across many files, this gets very expensive and very slow. In addition, if you want to fix any errors in your metadata that are in your NWB file, like we're dealing with an issue on Datasets 447 right now where a particular column name was named something that was invalid for the standard, and we didn't catch it. Fixing those errors involves downloading all the data I think it was like 300 gigabytes, changing about 20 bytes of each file and sending them all back to Dandy and creating a new Dandy set that has these small changes. And lastly, if there's no way to add on, append, and link, reference existing data, if you want to make changes, if you want to append new results and build off of other people's work. So your NWB file right now, if you want to include someone else's results, someone else's raw data, or like append to it, you basically have to copy the entire file and add your new stuff. But wouldn't it be nice if you can just say, all right, all of these data have been published, the raw data were published in this data set, and let's just link over there. Yeah. So building on what Ben has already mentioned, we've built LINDI based on Kerchunk and ZAR, and each chunk is stored in this way where you have a reference to the path of the data set, a reference to the chunk location, and then you have a URL identifying where you can access this particular array, a starting location, starting byte location, and how large is it. And this tells the APIs that we're building to go here, seek to this location, download this amount, and then decode it. And this, for our usages right now, these URLs have to exist somewhere. They can't just be on your local file system because no one else can access it. So an example, so this works, and some of you are already using LINDI as advised by the NeuroSift tools. It's fully integrated with NeuroSift, and so we can see how this works here. We're just going to copy. We'll copy this part first. Go here. Create a new notebook. Make sure it's clean. And here we're passing a URL to the Dandy archive. This is a particular NWB file. I forget which one it is. I think it's from Dandy set 363, and it's like 300 gigabytes or something. All right, so maybe it was smaller because this was pretty fast. We can import LINDI and call lindi.lindi-h5 file from HDF5 file, and this is an HDF5 file, and this will create a LINDI reference under the hood for this file. And then we can use PyNWB to open it. And it will, you can write commands after this and it will work all just the same. Right now, printing has a small error, but we'll fix that, so I'm not going to show that right now. But this LINDI file here only exists in RAM, and you can write it out to a file for later use. And when you do that, let's see, somewhere in here, you can see all the references are in here. This is kind of the JSON viewer of Jupyter. Here you can see this is the URL, which is located at the bottom of the file, the byte offset, and how much to read. And this tells you these are floating points with no compression, etc. And all of your attributes are in here. These are in volts. Your subject information is in here as well. And so all of the metadata becomes cached within this JSON, and all of the array data are basically pointers out to Dandy, and that can be read lazily on demand. And now because you have this, you've already generated this LINDI JSON file, you can read from this LINDI JSON file, and it will be much faster than loading the metadata directly from Dandy, and you can access the chunks still the same. So this works for the most part. And I was working with Steph earlier, and she was able to write this code here, basically which queries across all of the Dandy sets using LINDI files that have been pre-generated and stored on Jeremy's NeuroSift server to get all of the column names of all of the units tables in each Dandy set. So basically this is a little function that, given an NWB file on Dandy, just says whether the units are one of the variables measured. A little convenient way of testing that. But basically, we'll initialize a Dandy API client, iterate through all of the Dandy sets. We're going to skip a few that had problems, get the Dandy set raw data, evaluate whether the units table or the units are measured in a Dandy set, then find the first NWB file that has units, and then we're going to construct this LINDI URL using the Dandy set identifier and the asset identifier. And we're doing this because Jeremy's already cached or already created LINDI files for most, if not all, of the NWB files on Dandy. And then we don't have to do it ourselves. Then we're just going to load it. So this is a remote call that will download the LINDI file and then use it to read, to be passed into PyNWB to read. And then we'll just get the column names and store them in our dictionary. And this, let's see, works, pretty fast. And we're loading tons of NWB files that can be any size. They could be hundreds of gigabytes to megabytes. And we can pull the metadata from them very quickly because this metadata is stored has already been pre-cached in the LINDI file, and so queries on it are fast. So these are the kind of thing that you can do with the LINDI files is do an easy search across all these data. Okay, and then last thing I'll show is some work showing how we can append to a LINDI file. Let's say there's raw data on Dandy or even process data, and you want to process it in a different way. You want to run a different spike sorting algorithm. You want to run Zebra on it, and then you want to publish that to the archive, bundling your new results with the original data. That last part of publishing isn't done yet, but at least right now you can append to the LINDI file and load them together locally without duplicating all the original raw data. So here again, we will load a NWB file, and this time we're going to write it to a lindi.tar archive, a slightly different form than JSON, but allows for easier appending of new data. And then we can open it in PyNWB in append mode, create a new time series, add it to the NWB file, and write it out. And this will be fast because all we're doing is writing the new data, not the old data, and not duplicating the old data. And this new data, this tar file, will contain a reference to will contain the LINDI references of the original file, and all of the chunk references out to the remote archive. So then you can start appending and mixing and matching data from different sources. You could even create a LINDI file that is a composite of many different units tables or LFPs across thousands of NWB files and say, here, this is my training set for my machine learning algorithm. I can share it with you, and I haven't, the file is probably a few hundred megabytes because it's all references out to published places on Dandy. That's what I'm showing here. You have two data sets, raw data, process data, and you want to merge them into the same. Okay, so just to recap, we are actively trying to work to integrate this into the NWB ecosystem because of many different advantages, which Ben has already mentioned. Caching the structure, the LINDI JSON caches the structure, and the metadata allows for very fast access. You can edit the metadata, version control it easily. You can also use LINDI to cache data chunks locally. You can compose new files from multiple sources. They can be from different file formats, binary files, HDF5, ZAR, and we haven't tried it yet, but I think MATLAB files will work as well. And this is all compatible with PineWB, as was shown in the examples there. So yeah, we're working on better integration, both with the NWB software and support on the Dandy archive. You can't upload these LINDI files to Dandy just yet, but we're talking with them to support that. And we hope to integrate these LINDI with similar tools developed by the geosciences community. Turns out they have very similar problems. They're working with massive array data, simulations, and actual measurements from across the world. And they're sharing them on NASA's website, but mostly in HDF5. Turns out that's not the best way for them to access and compute on that data. And so they've built a very similar tool called VirtualizR and IceChunk. And we should join efforts and kind of build together with these other fields because they have similar, we can solve each other's problems. And as Ben mentions, there's pros and cons to this approach. It's easier to convert data to NWB because you don't have to do this copy. You can just add the map file. However, the resulting NWB data might not be optimized for certain read and reuse patterns. But we're wondering whether this optimization can be done by other systems after conversion, such as by the archive, and they can store various versions of these files. Yeah, and so that's it. Try it out if you haven't already. This might be faster for your searches across the Dandy archive to aggregate metadata or data. And it's already working well. It's in production use by NeuroSift. If you go to NeuroSift and search for datasets, you can download, go to the left. If it says using LINDI, which I think it does for almost all of them, you can click it and download the LINDI file, or you can construct the LINDI URL in the manner I showed earlier. Yeah, that's it. Yeah. So yeah, this is all, a lot of this is work in progress, and we hope that this will, we're aiming for this to be the next kind of version, the next backend to be supported by the NWB standard to help with all these pain points that people have, converting and reusing data. Okay. I haven't talked to them specifically about that, but okay.
Yeah, so I talked to Satra specifically about this. That the worry there is, one, he really wants to push people to compress data, and that data would likely be uncompressed. And two, they would rather push compute onto the user and not do all of the compute on the cloud servers. So like, yeah, you could solve that issue. You could solve the compression issue by having routines on the back end that automatically convert data for you into some compressed form that use the same mapping. But then that's going to be potentially very expensive compute.